So now let's talk about the typical design procedure for sequential system. This starts with how to specify the system. And then we try to build the state transition table, sometimes with the help of the state transition diagram or graph. And then we minimize the number of states in the state table, and then we do a state encoding, which is similar to input encoding. And then we select what type of flip-flop we want to use. Normally it's based on experience. And then we build the excitation table and output table. And finally, we do a combinational logical design to simplify the logic for flip-flop input functions, and then draw the logical diagram. So now let's show this design process using an example here. So in this example, we assume that we have already done the state transition graph here, and we have already minimized the state, we have already encoded the state. So the states, they're not called S1, S2, S4, they're called 00, 10, 11, 01, etc. Okay. And also we assume that we have already decided we want to use T flip-flop. So I'm going to show you that how we can build the excitation and output table based on the state transition graph and the flip-flops we're going to use. So what we do is we start from the current state. And with different input values, either 0 or 1. And then from this state transition table, we can figure out what is the next state. So for example, start from 0, 0. If input is 0, I move on to state 0, 1. So that is why I put 0, 1 here. Okay? And then for the next column here, the flip-flop input function. And I have the flip-flop input for A and the flip-flop for B. So for A, what I see here is currently I'm 0, and the next time I still want a 0. And I go back to my excitation table. I say from 0 to 0, the T input should remain at 0. So that is why I put a 0 here. But however, for the second flip-flop, B, it changes from 0 to 1. So from the excitation table, we know that to enable the T flip-flop to go from 0 to 1, I need to set the T input to a 1. So that is why I put a 1 here. So this is the way we try to build this excitation table and output table. Once we have this table, this becomes a combinational logical design problem. You have input, current state, and input. And then you want to determine these functions as a Boolean expression of the input. And these are the flip-flop input functions. These are the output of the circuit. So now we have built the excitation table and output table. So we can consider these two flip-flop input functions, TA and TB, and the output Y as a function of the input signals, current state A and B, and input X. And when we do a function simplification, we find out TA equal to exclusive of A and B, and then TB equals to the exclusive NOR of A and X. And we can easily draw the logical diagram. So the previous example, actually in that case, it is a completely specified state machine, which means that from any state, for any input, possible input value, we have a next state specified. What happens if the system is not completely specified, which we call incompletely specified? So consider this case. We want to have a system that generates the pattern 0, 1, 3, 5, 7 in a row, in a circular way. And we can easily build a table here with 0, 1, 3, 5, 7. We do the binary numbers for 3 flip-flops ABC here with their binary value. And then the current state, the next state. Current state, next state. And what happens with the design here? So when we want to use T flip-flops, we say, okay, you want to go from 0 to 0, I'll give TA a 0. You want to go from 0 to 1 for C, I'll give TC a 1. So this is fairly easy to build. This is the one we call the excitation table. And however, what happens with these 3 other cases? One flip-flop will be 2, 4, 6, which means A happens to be 0, B happens to be 1, C happens to be 0. That is the binary 2. In this case, the system doesn't specify what will be the next stage. So this is what we will consider as don't cares. So because the output is the don't care, so the flip-flop input function will also be don't cares. So now when we have all these don't cares, it will help us to simplify the Boolean function for these flip-flop input functions. In this particular case, we find out TA equal to B, TB equal to C, and TC equal to C prime plus AB. And we can draw the logical diagram in this way. Now the question is, once you have a digital circuit here, this circuit, they are not going to produce don't cares for your system. Whenever your system has a deterministic value, they are going to produce a deterministic output. So when we do a circuit analysis, we realize that in these three cases here, and their next stage, I first figure out the TA, TB, TC value either from this equation or from this circuit here, from this input. And it happens to be these three values here. And then based on the functionality of the T flip-flop, once I have a 1, I need to flip. So I got a 1, 1, and when I have a 0, I stay no change. So that is how I figure out this, do this circuit analysis. And in this particular case, I know the current stage, I know the next stage. I know the current stage, I know the next stage. I know the current stage, I know the next stage. For these three incompletely specified cases. What happens to the original system spec? When the system is at 2, it goes to 7. When the system is at 4, it goes to 5. When it is at 6, it goes to 3. So this is a good case because if the system starts with one of these unspecified system, after one clock cycle, it comes to this loop, and then it will stay in the loop forever. So in that sense, we call this system is self-correcting. And later on, we are going to see that by not specifying the systems completely, we are going to introduce security vulnerabilities.